Hi everyone, welcome back to my series on my senior project, a personal pick and place machine. So me and my team have finally decided on a title befitting a project of this magnitude that requires a little bit of skill out of all of us, and something that just wasn't so bland. We came up with a trip or try.p. This originates from the personal pick and place project. The three P's there. We kind of had triple P, and then we just shortened it up to try.p. And I made this graphic. I think it looks amazing. I'm absolutely excited with it. The University of West Florida's mascot, so to speak, is a nautilus shell, or I guess our symbol is more like it's a nautilus shell. So I implemented that into the P right there, and I'm just super excited with it. I think it looks great. I hope you guys do too. So now let's get into the actual premise of this video. So it's been a week or maybe 2 weeks since I last uploaded. Just been very busy with coursework and studying for my fundamentals of engineering exam and all of that good stuff. So I just haven't been able to really sit down and record anything because that just takes the longest time. Just because I'm not super comfortable in front of a camera and all that. So normally it takes a few takes, but I'm in the workshop every day, and I'm hard at work, just calibrating, testing, implementing our every feature that we want. So since that last video that I uploaded, I've been able to get a lot of work done, and I've got a lot of updates to show you guys. So let's hop into it. As always, just let me know if you guys have any questions on some of the stuff. I'm probably gonna be moving a little bit quick today, so if I seem to skip over anything, just ask me, and I can provide any sort of knowledge to whatever it is. So let's start here with this board that I created in KiCad. I ordered it last week, so it should be here in about a week. Ordered it from PCBWay. But this board aims to test everything that our machine needs in order to be successful. So it'll test all of our axes, X, Y, Z, and A being our rotational axis, as well as our component recognition feature. So we have two resistors of very close sizes. So in order to differentiate between those, it's got to be a very well trained program. So we have two resistors, one of metric 0805 and then the other one of 1206. Now these SMD resistors are going to be placed along this circle in varying degrees. So there you can see it'll test all of our features that need to be tested. And then I have a little ruler here at the bottom for our just calibration and really ensuring that we're down to that millimeter mark right there. So let's close these out. Now let's hop into the actual thing today, which is OpenPnP. There it is. Happy Pi Day to everybody, actually. That was funny. And give it a little bit of time there. I'm going to start up this camera. Yeah, let's get started. So you can see here in our camera view, let's go ahead and widen that a little bit. OpenPnP is a little bit funny in the way it displays images. So here in our camera view, I was able to upload and sort of it just took a little bit of work to get the dimensions right on this image here, but I promise once we get everything rolling, you'll see that it is our schematic that I showed you earlier. But this schematic in our camera view is going to be used to test and verify that all of our axes are working correctly, and I'll walk us through each of those. So let's start with turning on the machine. So here we've got our 24-volt power supply. I come over here, turn on our buck converter. Buck converter sends power to our tiny G, our vacuum pump, all that good stuff. So now that we have power, let's go ahead and turn on our machine here. So now that our machine is on, we can go ahead to our machine setup, our drivers, open up our console, and just run a couple of quick commands. Let's go Y10. There we go. G0. Oops, G0, X10. Okay, that works, I promise. It's just little quirk. I actually forgot about that. And then let's go A. So right now our A is at 0 degrees. Let's go ahead and move it to 90 degrees. Should end up right about here. There we go, perfect. Now let's send these all back. Let's go Y0, A0. Don't have to worry about the X because it didn't move. I actually forget. I can just jog the machine right here. There we go. Sorry about that. Just a little bit quirky at times. Definitely a little bit newer to OpenPnP and all that. But absolutely love the program. It's a great program. Just a little bit of user error on my fault. All right, so let's go ahead and open up my recent job. Try p.job. Now you can see here I've got all of my placements from the board that I showed you earlier. So KiCad has a very nice feature where you can actually import these placements into OpenPnP. So I've got all of these placements. They are relative to this origin here, this small red circle with a cross through it. So that's our origin. That's what all these placements are based off of. So let's just hop right into it. Actually, let's go for it. So let's go ahead and set our machine at the origin that I just mentioned. There we go, nice and easy. Now let's run through our fiducials. So this is going to sort of outline the board. The fiducials are actually very important for this feature here. Perform a fiducial check for the board and update its location and rotation. So whenever we go to actually implement the actual physical board that I ordered, of course we can't get it perfect, you know, at the machine's origin or anything like that. So the machine's going to kind of have to find it. So that's why you perform this. The machine is going to go to a location that you'll probably have to jog it yourself, but you'll kind of jog it over there, and then it'll see that fiducial, and then from there it'll lock onto it, and then hop to the next one where it thinks it is, and it'll perform each check and update the coordinates of everything, so to speak. So now that we are at the origin, all of these placements here, you can see that X is 2.7, Y is 2.5. We have a rotation of 0, but we're at X15 and Y12. So, you know, that would put us back, right? No, all these placements are actually relative to the origin. So let's go ahead and hop down here to resistor 1. And you'll see that it actually moves to resistor 1, not backwards. So let's hop back to our fiducial. And let's go ahead and outline the board here. Nice. Alrighty. And then I forgot to mention, I do have my amp meter set up in the background, so we can just make sure that nothing is drawing too much current or, you know, we're not on the edge of failure. So during my testing, everything was perfectly green. I think the max amps I pulled was around 3 to 3.5, somewhere in that range, which each of the channels on the buck converter can handle up to 3 amps. So 3.5 divided up, obviously not equally, but divided up among those 4 channels puts us well in the margin. So now let's hop through all these resistor placements. You'll notice that these resistor placements is where we start getting varying degrees. You can see here resistor 2 is 135, resistor 3 is negative 90. So this is where you'll see this A-axis over here start moving. So let's go ahead and hop in there. Now I'm just going to run through these rapid fire. Alrighty. Everything came back good. Now let's head back to our origin. So you'll see there that everything lined up perfectly with the schematic and the image camera, which is excellent. I mean, this is exactly what we want right now. This just tells us that the X and the Y are perfectly coordinated. The A seems to be perfectly coordinated, although there's no way for me to actually test that as, there's no actual way for me to, I can't actually see or how the component's being rotated. So that's all good. Of course, our Z-axis is not set up yet, so waiting on the mechanical team for all that, but they're making some good headway. But I did have a feature in place. So my feeder system, we plan on implementing back here. The feeder system is obviously going to be at a different level than these components. So I actually have the Z already set up for something like that, just to make sure that the Z is working. So if I come over here, this is the default strip that OpenPnP gives its user. I just edited the coordinates of the strip. So let's go over here. I actually need to update this. It's no longer 260. Let's just say it is 230. Let's be safe. Let's say go with 215. Just be real safe and moderate right now, as I have been updating the machine, so I don't quite know exactly where that would be without doing some more tests. So let's go ahead and head over to our feeder. So, sorry about the wires. If you could see, our Z-axis did move. I'm going to move the machine back to the origin, so you see this move again if you didn't quite see it. But, and there it is. So you can see that that axis is working properly. Now it is not quite coordinated. I can't coordinate it without knowing our rotations per millimeter and all that with however we configure the axis, whether we want to go with some sort of linear rail or maybe a lead screw, who knows. We're still talking about all that. But yeah, that's all of our updates. I did show you guys the pump last time. Let's go ahead and just show that again, because I did replace the motor driver with a relay. I think it looks much better now. I think whenever we move into our final implementation phase, where we actually get all of the circuitry and stuff onto the frame, this will make it just so much easier. So go ahead and we'll turn on this pump here. There we go. Now we've got nice vacuum being held. Go ahead and there we go. So right now with the pump on, we are pulling 312 amps, or sorry, microamps, and under load, little shy of 400 microamps. So that's all good. Real quick, I'll actually just run through just a couple movements with the pump on, so we can see where the power usage is with all that. If the camera will stay still, of course. I got to do things kind of funny in the lab sometimes, so this isn't quite perfect. I will hop back whenever I get this fixed. Okay. All right, so we're back. We have the vacuum on, and let's go ahead and just run through just a couple of placements and give us an idea of where our machine's sitting at power consumption wise as a whole. So I'm going to initiate a move that moves all of our motors. That one would be our feeder. So let's go ahead and move here. You can see there for a second we got up to about 3.2 amps. Let's go ahead and head back to our origin. Got up to 3.1. Now let's say we're under load. Now let's go ahead and move back. All right. Same thing, it was about 3.2 amps. So hopefully you guys could see that. So all in all, I mean, we are looking quite good power consumption wise, axis wise. The last little bit that we need, let's go ahead and turn off this pump. The last little bit that we need is going to be obviously our z-axis actually being integrated, and then our camera vision. And then I would say this project's just about there, guys. Just about there. I'm gonna go over here, grab our pick and place head, show you guys what this looks like. Just because whenever I was researching this project, I actually couldn't find how people were making their heads. Come to find out, you can actually just buy one online, and it's incredibly neat. So you have a linear rail here on the back, so you can see. I'm sure our head will actually sit somewhere down here, so it can slide up and down on this linear rail. We'll probably have it belt driven, I assume, and it actually has a very neat sensor on the back here. There we go. Very neat sensor on the back that'll actually tell us when we hit that 0-degree angle. So very interesting. Highly recommend. I can give the link out to whoever would like it. But yeah, so we need to implement this, our camera, and I'd say we're just about there. So thank you guys for watching, and yeah, let me know if you have any questions.